Okay, so I want to discuss a bit more intuitively about these two concepts. I think there's a lot of material about it. So the Cramer-Rao basically answers, it only deals with unbiased estimators. So we mean here where we have some true parameter theta we want to estimate, and we're going to take the expectation of our estimate and expectation of theta. And the reason why this makes sense is because theta hat, it's an estimator. It's applied, we receive some data x1 at xn, and we throw theta. So theta hat is some function of x1 at xn. And so every time we get a new x1 at xn, we'll get a new theta hat. So it makes sense to have theta hat's going to have a distribution. We can look at the expectation, is the idea. So that's the idea. And the idea is, well, let's look at all these estimators to which theta hat this is true. And let's what is the answer to the question, what is the smallest variance? All right, so that's the question. We know it's unbiased, and we know now the variance is the same. Now the mean squared error will be the variance, and we want to attack this question. And Cramer-Rao says, well, it's going to be basically for some random variable x, right? It's going to be basically, we're going to say the variance of any unbiased estimator will always be at least 1 over n times the Fisher information. So where we have some sample random variables x1, xn. And so where this is drawn from some sort of some density with some parameter theta. So it basically says more or less that regardless of what, this could be method MLE, MOM, assuming it's unbiased, for any of those, the variance will always be at most 1 over n times the information. It makes sense because as we have more random variables here, we're basically saying the variance could be lower. So that's the idea. Just useful because, again, we want to minimize MSE, so this is quite useful. Okay, so that's the Cramer-Rao lower bound. And basically, if it achieves it, well, we have an unbiased estimator plus minimum variance, so we're going to call this minimum variance unbiased estimator. So if it's achieved, sometimes there'll be minimum variance unbiased estimator is the idea. Okay, now we're going to go into Fisher information, which I think is a really, really, like, maybe it's not, like, I just think if you could understand it, like, understanding the expectation part in this intuition is very important for other fields. So, like, for example, in conformal prediction, a lot of times, understanding what expectations and probabilities are. I think many times we just write this out, but don't really understand what it means. It really means we're not dealing at all with specific data. And especially in probability, when we make a probabilistic argument, it's in probability, so over all the randomness in X. So it's sort of similar in conformal prediction and a lot of other statistical fields. Okay, so maybe it makes sense to first sort of write out what the Fisher information is, and then I'll go into this intuition here. So the Fisher information, it's called I of theta. So it's a function of theta. So it's going to take in a theta, and it's going to be the negative, well, this is one way, which I like this way better. Negative the expectation with respect to our data of the curvature, so the second derivatives, the second derivative of the log likelihood of, let's say, some random variable x, not y, x given theta. Yeah, so this is sort of a mouthful, but let's see if we could unpack it. So let's let's just sort of build this from the ground up, okay? So what is this? So let's say we receive some data, x1 and xn. So this is well, let's say we have capital random variables, and then each of these we receive some realizations, x1 and xn, right? And these are drawn under some theta, unknown theta. And the idea is once we see this, we could plug this into some density under some theta value. And we know, basically more or less, this is the likelihood of some theta given x. Once we plug in the xn, we get some theta, and then we could get some plot where we'll have theta, and then likelihood of theta given x. Right, so, and then we have something like this. And the idea is well, let's find the theta that maximizes it. That's MLE. But the idea here is sort of, we're going to have, this is now, once we plug in our x1 and xn, it's a function of theta, which makes sense because that's what the information is, the Fisher, and we'll take the log, and it doesn't matter. We'll just take the density, and this is some function of theta, and this will still be some other function g of theta. Okay. Okay, so that's if we were to see some sample, x1 at xn. That's if we were to see some x1 at xn, we plug this into our density, we take the log likelihood, and we get some function of theta, right? Under this specific realization, x1 at xn, what are we going to do? Under this specific set of realizations, under some theta, right? It's a function of theta. So let's say we do theta MLE, like this theta here. So we'll call this like theta that we're going to think about it. We could do any theta, but let's take this theta. Let's call this theta equals MLE, theta equals theta star MLE. So basically, find the theta that made our data most likely, we're going to take the curvature, right? So at this theta, we're going to take the curvature, right? Which is fine because this is some analytical function of theta. We're going to take the curvature at this specific theta. So we're going to take the curvature, right? We're going to take it at this theta, and then we're going to take the negative value. Hopefully that makes sense. So we receive x1 xn, we plug that into our density. This is some function of theta. We take the log, and we get some plot like this. And then all we're going to do is add some specific theta value, which is the input argument to the Fisher information. We're going to take the curvature. Okay. But again, that's like if we were just doing this part under some sample x1 xn. That's if we were to just do that. But the key part is that it's with the expectation here. This is the really beautiful part. And this expectation part makes it the information that some random variable gives. So if you go to like Wikipedia, for example. Right, wait, let me maybe even do here. So like, let me say Fisher information. Because I think this is just so important. In mathematical statistics, the Fisher information is a way of measuring the amount of information that an observable random variable x carries about an unknown parameter theta of a distribution that models x. The Fisher information is a way of measuring the amount of an observable random variable carries about an unknown parameter theta. So it's like the probability that we observe given a known value of theta, right? So we condition on theta. If f is, so the curvature, right? So the idea is we have some function of theta, and we condition on that. And then we take the curvature of the log likelihood and expectation. Okay, let's see if there's anything else. Okay, I'm going to just go back here. So that's the idea, is that this is the expectation over all possible samples we receive. So we got some samples, x1 and xn. And so like you can imagine we have like basically some k by n matrix where k is the number of experiments we're going to rerun this. So we get another sample x1, xn. We plug this through the density, again, log density, and we'll get a slightly different curve, right? Maybe it looks something like this or something like that. And we're going to do the MLE, and we'll get something like this maybe, and we're going to take the curvature again, the negative curvature. And we do this like a bunch of times. We go through this for all possible an expectation, right? And all possible x. So you could imagine like we do basically like some Monte Carlo estimate here, right? And we could just take in like this. Like we could just, that's the idea. And you're just taking the average curvature. And here we're going to just take the expectation. So that's the idea. Over all possible samples x, you plug it through your density, add some theta, and you take the curvature. And so that's like the idea. So it's really beautiful understanding the expectation part here. That's why it talks about of a random variable x, of some random variable x, not a sample x. And what's important here, I guess, also is that, what else I was going to say? Okay, yeah, so the intuition. So the intuition is, like, let's say we're doing the MLE. Like, let's say we have I of theta MLE. So we want to put in the MLE estimate of some like, let's say it's some Bernoulli. So, right, so theta star MLE. So like if x1 xn comes from some Bernoulli theta, right, maybe we plug in theta star MLE just to be, some I xi over n. So this is what we're interested in. And the idea is, well, let's just consider different curvatures here, right? So we could have something like this. So let's say this is theta MLE versus maybe something like this. And so the idea is, right, the whole point of MLE is like, under this data, how likely is our data? So if like, even let's be more extreme, let's say our data is like something like this, or I don't know, something like this. If our data is like this, more or less what it's saying is if we were to slightly change our theta MLE, if we were to slightly change it, so like sort of when we think about it in our density here, if we were to slightly change the value, or here, right, if we were to slightly change our theta to which our data x was drawn from, it would be so unlikely to receive x. There would just be a huge drop off in how likely this would be. And that's why we want there to be a strong curvature, because it's basically saying our data, or in general, our data super strongly supports the idea that this is the true theta that drew our data. If our data is like this, it's saying, well, all these values, all these possible theta values basically gave us the same likelihood to draw our theta. So again, it's like hard to do this because for here, it's some actual realization x1, xn. But if you, I guess, plot I of theta for different thetas, if you were to take this like an expectation, like which is what this does basically, and plot it across I of theta, the idea is that basically that all these thetas basically make our data as equally likely as possible. So the theta MLE is like just one value that isn't really, like there's many plausible values about the random variable. On the other hand, the more peaked it is, it's saying that we believe just so strongly that this is actually the true theta. So this is like the true parameter that x1 at xn was drawn from. If this makes sense. And I think so that's like the idea, and it's a very nice idea. And I guess my point is it's understanding really the core part about statistics in this is like, again, it goes back to this method of moments where you need to really understand about that there's this population that we don't see, and there's our realizations that we do. And so the method moment's so beautiful because it sort of like really attacks that, because, okay, we have our expectations here. That's not about x1, xn. That will give us some function of thetas, right? Because it's truth. And now we have some realizations that are drawn from some theta, and that we could now estimate theta because of these realizations. And it's the same thing here where we're going to take this expectation here, and that allows us to talk about the random variable, not any sample. And when we, I think, talk about p-values and stuff, we get a specific realization. But because we're thinking about some general random variable distribution, we can now talk about in probability over many different realizations of x. Even though we don't only see one, when we're able to sort of talk about the population, it allows us to talk about things we can't see.